Hi everyone, distinguished professors and teachers, ladies and gentlemen. Thank you for listening our Defense for Senior Design. Our project name is Multi-Sensor Data Fusion for Wearable Respiratory Rate Monitoring Microsystem. We have team members of Wenwen, Peixuan, Jiang, and me, Hongdan, Yang. All of us are from EE. Our advisor is Dr. Cao Li. Totally, we have 4 parts to introduce, and for the first part is a project introduction. Respiratory rate monitoring is a significant indicator of physical condition since it's an important marker of serious illness. Methods like using movement detection, respiratory belt transducer, and PPG sensor have been developed to realize RR monitoring, but the accuracy for certain application scenarios need to be improved. In this project, 2 separate sets of real-time monitoring data can be obtained from the preceding project. We propose to use a combination of microphone and PPG-based sensors to improve measurement accuracy for RR monitoring. First, it's a research project approved by Dr. Cao Li. At the literature review stage, the main methods we focus on at the very beginning are some mainstream sensor fusion algorithms. We decided to choose common filter as a primary approach after analyzing the existing data. A new variable relevance coefficient is introduced to increase the reliability and accuracy of common filter. Chest belt sensor output is used as reference data. Scenarios without and with reference data are considered, while the former one is the most common case. For this case, implemented common filter makes the project more accommodating. Moreover, the scenario when some reference data can be made available for training a data fitting algorithm by multiple linear regression is also built to make the fused data more reliable. Then we introduce the basic idea of common filter. We define ZK as a kth measurement result. In order to estimate its actual value, we need to start with its average value. And we define xk hat as an estimate value. After some simple calculation, we can get the equation shown on the right side. Then try to define kk as 1 over k. We get the final core equation of common filter, which is marked with a red box here. During the whole project, we define parameter x1 as microphone data and x2 as oximeter data. For evaluating the fusion effect, reference data are also included to calculate the error factors by using the thought of correlation coefficient. More definitions, which are used for the next comparison part, are shown here. Now, let's welcome Peixuan Jiang to explain the method of data fusion without reference data.
Hi everyone, this is Peixuan Jiang, and it's my pleasure to introduce Part 2, Data Fusion without Reference Value. First, for 1 to n data points and a recursive process, we can define the common game k and related parameters. Then we can update the estimated error in each recursive process by the equation at the bottom. Then we apply the recursive equation of the original common filter algorithm. But in the plot, you can see the fused data cannot track the right path. Since for our project, there is no mathematical relation between x1 and x2 to build up the state equations. Therefore, we have to make some improvement here. We optimize the common filter recursive algorithm with relevance coefficient f as following equations, where f is determined by the relevance between the real-time data x1, x2, and the state estimate of x1. And we introduce Mahalanobis distance to express the relevance more efficiently. Mahalanobis distance is a measure of the distance or deviation between different datasets, which illustrates their relevance. If the math points are close to each other, then the datasets A and B are related. First, we can use this score to standardize the data and then build the covariance matrix. And finally, we calculate the Mahalanobis distance. We can see the process clearer with flowchart. For datasets x1, x2, and state estimate, we standardize them and build the covariance matrix S. Then calculate the distance d. And finally, we construct the triangle and calculate the relevance coefficient f with projection I1 and I2. In the recursive equation, you can see if I2 is relatively big, then it means real-time data x1 are more related to x2 than state estimate. So we choose to believe more in x1 in this recursive process. then f is close to 1 and 1 minus f is close to 0. So the proportion of real-time data x1 is increased while the estimate is decreased. This method helps us to determine the weight factor of datasets more precisely and effectively. And in the plot, you can see the real-line fused data is combined reasonably and follows the tendency of the respiratory rate data by oximeter and microphone in a well-predicted path. And the error factor is also small, which proves the validity of the algorithm. Next, we have Wenwen to introduce the data fusion with reference.
Hello everyone, I'm Wenwen. Now I'm going to make an introduction about data fusion with reference value. To begin with, we calculate the correlation coefficients of these three datasets, and by observing the results, in our project, the correlation coefficients are greater than 0.8, and we can conclude that those three datasets have a strong linear correlation. Therefore, we use a method called the multiple linear regression to make the data fusion. As for the multiple linear regression, it is a statistic technique that uses several explanatory variables to predict the outcome of a response variable. The goal of MLR is to model the linear relationship between the explanatory variables and the response variable. As for the first 100 training data points, we can use the following commands in MATLAB to calculate the fixed coefficients beta. And for the remaining data points without reference value, we replace the term xref at the left side of the equation with the fused data y. The equation on this slide shows the results of our model. Please take a look at our results. There are 4 curves, and also we calculate the error factors of these 3 datasets. As for part 4, conclusion, this slide shows the error factors we calculated for different datasets, and the error factor between fused data and the reference data are in the middle of error factor between 2 individual obtained data from different sensors and the reference data. Since we only have 2 input data without reference, the error between reference data and one of them is relatively big, while the other one is relatively small. This will leave the error of our fused data located in the middle range. The error factor between fused data and reference data is the smallest one among the 3. With the impact of reference data, we obtain a most convincing and accurate fused data. Apparently, the error of MLR result with reference data is smaller than that of common filter without reference data. Since the reference data can provide the weight influence factor, however, the method 1 contributes to increase the scenario adaptability of the algorithms. By building 2 separate data fusion algorithms with and without reference data, this design is capable to handle more application scenarios, and the traditional common filter is optimized with a newly introduced parameter, which is Mahalanobis distance. And the plot shows great fused results which corresponds with the designed algorithms and shows their validity. The machine learning can be promising approach for future work by using the large amount of sensors and reference data to train the algorithms. This slide shows the team members and acknowledgements, and this slide shows the reference. Thank you.